So welcome to video 12D on restrictions and determiner phrases. So in this video, we're gonna look at how and why we should symbolize every F as G, and every frog is green, or what have you, and why, and what it is about the different parts of the English that go into the different parts of the symbolic symbolization, the logical symbolization, and a big part of understanding how the different parts of English go into the logical language is understanding what the different parts of the English language are. And there's an important, these notions of restrictions and determiner phrases are going to be important in understanding the different parts of the English and what they're doing. So we're going to start with a simple English sentence and its grammar. Bob chirps. So this sentence breaks down into two parts. It breaks down into Bob, and it breaks down into chirps. So two parts, very easy. Hooray. Now I have a slightly more complicated English sentence. And if we were going to break this English sentence into parts, we'd do it like this. We'd say that one part is every emu, and the other, which has its own parts, every and emu. And we say the other part is chirps. Okay? It seems pretty obvious. But note that that means that natural language quantifiers are grammatically distinct from logical quantifiers. Why? Well, so the natural language quantifier phrase, every emu, that goes where a name goes. It goes where Bob chirps goes. But remember, in the logical language, we have FA. So A is the name. We don't put some X where A goes. We put some X in front of the formula. So that's a way in which natural language quantifiers are different than logical language quantifiers. And there's another sort of way they're different in terms of the grammatical rules. So in English, you take a quantifier like every, and you give it a noun phrase like emu, and those together form a quantifier phrase. And then you take that quantifier phrase, and you add a verb phrase like chirps, and you form a sentence like that. And that's very different from the grammar of a logical quantifier. As I already discussed, logical quantifiers do not go where names go. They go at the front of formulas, not after predicates, or next to predicates. Whereas in natural language quantifiers go where names go, and the grammatical rules are different. A quantifier in the logical language hooks onto a formula and makes a new formula. In natural language, quantifier hooks onto a noun phrase like emu to make a quantifier phrase, and then that thing attaches to a verb phrase to form a sentence. So to get from a quantifier to a sentence in natural language, you need two things. You need a noun phrase, and you also need a verb phrase. Whereas in the logical language, you only need one thing. You need a formula. So we sometimes call logical quantifiers unary, meaning they hook onto one thing to get to a formula. And natural language quantifiers binary, meaning they hook onto two things to get to a formula. So those are two grammatical differences, and there's also a meaning difference or a semantic difference. So everything is a mammal tells us that each thing is a certain way, namely a mammal. Every whale is a mammal says the same thing, is a mammal, but it only says it about the whales. It doesn't say it about everything. And so the claim is restricted to the is a mammal claim is restricted to the whales, and that weakens the claim. You're not making a strong claim anymore. You're saying, well, I don't know, everything is a mammal, but all the whales are. And that's another important fact about natural language quantifiers, is that they almost always have a restricted range. The quantifier concerns not all objects, but a certain subgroup of objects. Whereas logical quantifiers don't work like that. They have an unrestricted range. They concern all objects. Again, in different ways, the existential or the universal. But either way, they look at all the objects to find out if there is at least one or all have a certain property. Whereas natural language quantifiers only look within a certain group to see is there at least one thing within that small group, or is everything within that small group have a certain property. So what this means is we're going to have some grammatical divergence. As I said before in the very first video, and I'll say a little bit at more length. In chapters 1 and 2, if you have an English sentence and you have a logical language sentence that symbolizes the English sentence, then the trees are going to have the same shape. They're going to have exactly the same structure. And they have different elements at their nodes. In the English case, we have words and phrases and sentences. And in the logical case, we have sentence letters or logical symbols. But then the logical symbols are just straightforward symbolizations of certain English words and phrases like if and then, and or, and if and only if. And then the sentence letters of the logic are just symbolizations, are just pair up with atomic sentences of the English language. Okay, that's all gone, or it's going to be gone, as we'll see in chapter 3. The tree of an English sentence has one structure, and the tree of the symbols, and then you have the symbolization of the English sentence, and that tree is going to have a very different structure, and that's going to make symbolizing more difficult. So let's get into that. Let's look at an English sentence in more detail, and we'll look at the logical sentence that symbolizes it in more detail, and see why their trees are different, and we'll also see why it's a good symbolization nonetheless. So here we have every emu chirps. So we saw we can break that into every emu, and we call that a determiner phrase or a quantifier phrase, and it's what we're talking about, the subject. And then we have the verb phrase, which in this case is just a simple verb, chirps. And it's what we're saying about the subject of the determiner phrase. So the determiner phrase gives us the topic or subject, and then the chirps, the verb phrase, tells us what we're saying about it. So we have two pieces. We have the determiner phrase and the verb phrase. And the determiner phrase itself breaks up into every and emu, as we saw. And it has two parts. So there's the quantity or determiner word, that's the every in this case, and that's why we call it a determiner phrase, because it has a word that determines what quantity of things we're talking about. And then we have a noun phrase. In this case, the noun phrase is just the noun emu. And that means we're talking about the emus. So that noun phrase there is what's doing the restriction. It's what's restricting us from, we're not talking about everything, we're talking just about the emus. And so that's an example of where the English quantifiers work differently than natural language quantifiers, because the English quantifier here hooks onto a noun phrase that shrinks down the group of things that the quantifier is talking about. And we're applying the verb phrase to every single one of the things in that group. So the noun phrase specifies the group, the where the restriction is. The determiner word says what quantity of them are we ascribing a property to, and the verb phrase says here's the property that we're ascribing to some or all of the objects in the specified group. So again, we know that quantifier plus noun phrase gives us a quantifier phrase or determiner phrase. The quantifier phrase plus the verb phrase gives us a sentence, and that quantifier phrases go where names go. And that we have this semantic fact that, or a fact about meaning, that the quantifiers concern a subgroup of the objects, not all of them, in that case the emus. And that restriction is accomplished by the noun in the quantifier or determiner phrase. Okay, so we've looked at the sentence every emu chirps a little bit, and we've talked about its grammar and how the different parts of the sentence contribute to its meaning when it does. But that doesn't tell us by itself how to symbolize the sentence, because we don't have in the logical language a quantifier that works the way every does in natural language. We've seen these grammatical and meaning differences. So we should think a little bit more about what every emu chirps means to figure out how to symbolize it. So you can imagine that all of the emus are in this circle, and if you're outside this circle, you're not an emu. And that all the things that chirp are inside this circle, and so if you're outside that circle, you don't chirp. So everything outside both circles is neither an emu nor a chirper, and in the area where they overlap, we have things that are both emus and chirpers. And now we might imagine, or might consider, well, suppose we want to know whether or not every emu chirps, and we just look at objects in the different categories and we ask, is it a problem if there are objects in these different categories or not? So if we look over there on the left, we would find things that are emus that do not chirp. And if there are any such things, then every emu chirps is false, because they would be emus that don't chirp, and that's what every emu chirps says there are none of. In the middle, we find things that are chirping emus, and they're no problem for every emu chirps. If there are things there, yeah, that's just fine. But it's also fine if there are things that chirp but aren't emus. Right? Lots of other kinds of birds can chirp, and that's fine with every emu chirping. And finally, it's not a problem if there are things that neither chirp nor are emus. It's perfectly consistent with my existence and chirpiness is perfectly consistent with the truth of every emu chirps. So it's really only a problem if there are, if we look and find that there are emu non-chirpers, then we have a problem. So we could represent it like this. The circle of emus, however big it is, has to be entirely within the circle of chirpers. Or you could think of it like this. If EX means is an emu and CX means is a chirper, and we find something that is both, that EX is true of and CX is true of, is that, have we then found a counterexample? And the answer is no, that's okay. On the other hand, if we find, right, so we want to figure out, you know, if we take EX and CX up to a thing, and they're both true, do we want to say that, what we need to find, so remember, our universal quantifiers hook onto formulas, so we need to find a formula where we want to say, if that's true of all of the things, then every emu chirps. And if that's not true of all the things, then it's not true that every emu chirps. And so we can start by considering, well, if the truth values of EX and CX are a certain way, then should the truth value of that larger formula to which we're attaching the quantifier also be true? And so if EX and CX are both true, then the whole thing should be true. That formula that we're going to attach the universal quantifier to. If EX is true but CX is false, then we have a counterexample, and so that formula that we're attaching the universal quantifier to, that should be false. And if we have EX is false and CX is true, that's okay. So we want our formula to come out true. And if we find a non-emu, a non-chirper, that's okay. It's fine if that formula is true. So what this looks like is saying is, okay, we carry this formula around to each object, and we ask, are you an emu and are you a chirper, and we get answers back, and then what we need is a formula that has these truth values, T, F, T, T, when emu and chirp have those truth values. And the formula that does that is if EX then CX. So if EX then CX gets the right truth value for objects in each of the different categories. And that's why we'll symbolize every emu chirps as for all X, if EX then CX. Now, it's important to understand what's involved in this, though, because remember that if P then Q, that's equivalent to not P or Q. And that means that for all X, if EX and CX is equivalent to, for all X, either not EX or CX. Now, that's true, not EX or CX is true if there are no emus, because the left disjunct is always true. And so for all X, if EX then CX is also true if there are no emus. Now, it's not obvious that every emu chirps is true if there are no emus. This is debatable. I'm not going to get into the debate right now for time reasons. There are reasons to think, in fact, yes, it is true if there are no emus. There are also reasons to think, no, it's not true if there are no emus. We're going to assume that every emu chirps is true if there are no emus. So we can basically think that there are two scenarios where every emu chirps is true. There's the scenario where there are no emus, and then it's true. And then there's a scenario where there are emus, and then each of them is a chirper. And we're just going to treat every emu chirps as working in that way. So if we look then at, we have our English sentence, every emu chirps, and we can divide it into the determinative phrase and the verb phrase, and we can see how the different parts of the English sentence go into the the logical sentence. The determinative phrase, every emu, gives us the universal, it gives us the connective, and it gives us the CX. And chirps, nope, it gives us the EX. So every emu gives us the universal conditional EX in the antecedent, and chirps gives us CX in the consequent. How you think about the variables is hooked up. You can do it either way. So if we draw it like this, the quantity word is giving us the every. The quantity word every gives us the universal. It gives us the arrow, and you can think of it as giving you the variables. The noun phrase from the determinative phrase, in this case, so emu, gives us the antecedent, now fx, and the verb phrase gives us the gx. And so there is still a correspondence between the English language and the logical language, but it's more complicated. Right? There's no one part that every hooks up to in particular. It gives us a bunch of different stuff. And then we plug the emu in one place and the chirps in a different place. And so, as you can see, there is a correspondence, but it's more complicated.